All right, so we begin with another coding challenge today to try to fail one more time. This stream is for entertainment purposes only. And let's see what we've got today. So it's the previous problem. Interesting. So, let's see. What's the random challenge today? Pick one. And again, hard. No? Easy! Finally! Oh gosh, finally. I thought after 9 hours of programming today, I will program another for another hour. So, subtree of another tree. Should be straightforward. Everyone loves it, so let's see how fast we can solve it. Given two non-empty binary trees as an T, check whether the tree T has exactly the same structure and node values with a subtree of S. A subtree of S is a tree consists of a node in S and all of these nodes descendants. All right. So is everything fine with the internet? Yeah, my internet here is always sucks, like the entire Wi-Fi. All right, so a subtree of S is a tree consists of a node in S and all of these nodes descendants. The 3S could also be considered as a subtree of itself. The 3S could also be considered as a subtree of itself. Example, given 3S, so we have this 3, 4, 5, 1, 2, given 3T, 4, 1, 2, return true because T has the same structure and node values with the subtree of S. All right, so we start parsing S. I would imagine we should do breadth search first until we find the tree. And once we find it, but this is a binary, right? It's not balanced though. So the problem, so it's not binary search tree, unfortunately. When it's binary search tree, we can quickly find an element here. In this case, no. In the binary search tree, you can just say, okay, your T root value starts with 4, so the root node is 3, so we go to the right. Then let's say we have 6, or let's say 5, right? So we say, okay, this will be left of the 5 because it's less than 5 and greater than 3. So we quickly find it. But because this is random binary trees, it doesn't work like this. So we need actually a very easy solution. So again, we start with BFS, we find the node because we have no idea where it will be. Once we find the node, unfortunately, this part will be linear. And once we find the node, it's still linear. So there is only linear solution here. Yeah, in example 2, when it falls, right? Because we have 0 here in the S and it's not subtree. And if T is only one element, it's okay. It's also fine. All right, so let's switch to the whiteboard. Again, a little bit of magic, although I would say I already know the algorithm. Basically, is it round? Okay, duplicate. Nope, it's not. Oh man. Let's say for simplicity, we have only 3 like this. So this is 3, 2, 1, and this is 4, right? This is S, and then the T would be and let's put it in red. So it will be 2 and 1, right? So, oops. So basically, the algorithm is straightforward. Step 1, right? 1, find root of T in S. And then 2, recursively or maybe in BFS manner, whatever, traverse both S and T. So the complexity we're targeting linear one, I think, because they're not binary search trees. There's no guarantee. I don't think we can do better. Right. Let's switch back to our coding part. So the first step, right? First find root of T. Also, let's quickly verify the inputs here. Yeah, there are no inputs. They say they're non-empty. They're non-empty. We have value left, right. Okay, got it. So I'll start with the queue of 3 node queue. We insert in the queue. So basically, we start with the breadth first search, right? Do we want breadth first search? Just wonder. All right, let's do this breadth first search. While queue empty, right? We do simple stuff. We just basically say 3 node next equal to queue top, queue pop, and then we check if next val equals to what? To T val, then Second, traverse both. Traverse both to verify they are equal. I'm not quite sure if, so I would imagine multiple nodes may have similar values here, so we never know which exactly one is the right one. So why not just say that we have some, we can make it private here. So basically we'll also return Boolean are equal, I equal trees, and we still have same st as an arguments. And all we do is say this: if s equals now ptr and t equals now ptr, right? So this is first condition. Or the second condition would be s wall equals t wall. Then we return okay, no, let's not mix this stuff. Let's say this as else if, right? So here we return true, right? Return true. So both stopped. In this case, we return I equal trees, s left, and t left, and I equal trees, s right, and t right. So this portion and else, so if they're neither, so they're not now pointers, right? And let's say only one of them is now pointer. Ah, uh-huh. Mm-hmm. So the problem with this, if then we need to check if they're not now pointers actually. Whatever, let's do this. If this not now pointer and this now pointer, btr, and let's clarify it like this. So if this not now pointer, this not now pointer, and their value are equal, then we check subtrees, because it can be one is now pointer, another one is not. So this fails, right? So we never go here, but then we just check values and we got this now pointer exception, whatever. So if let's say values are not equal and one of them is now pointer, right? Then we return obviously false. False. Correct. So the only thing which is left to check is basically this. So we start with values here. Should I just say are equal trees, because we will basically check exactly this and start checking their subtrees, so we don't need to. Yes, exactly. Cool. So all we need is to try to are equal trees next and t, right? Return true, else what do? Else we add to the queue left and right of s, of the next, sorry. Queue, insert, we start, let's say, with left, and then go to right, right? S, sorry, next, left, and right. If we are unable, if the queue ends, we cannot find anything, right? Then we return false at the end, right? Should work. And because I'm super tired, I will do my favorite. I wouldn't use examples to verify code first. I would just use my favorite error-driven development and just run the code and debug it like this, yeah. Is it push? Maybe it's push. I never remember this. Let's try push. Now we have some suggestions from prior examples. Interesting. This should be top and then pop. Oh no, this should be front. Sorry. Not the top. Top is for priority queues. This is just regular queue. This is basically BFS-like. BFS-like main tree traversal. Let's see. First of all, this shouldn't be empty. Oops. Yep. And let's also do this, so it's more, and then I'm like this. Right, should work. Let's submit and see where it fails. Yeah. Else if. So we check for now PTR here, so it doesn't really matter. But for this one, we just need to say next. No PTR. Right. So run code should pass as usual, and then we click submit. Hey, faster than 86%. Memory is awful. Yeah. So the amortized complexity should be linear here. The asymptotic one, technically, so this goes n, right? So this one is ON, but the problem is this thing is also theoretically or n. But the thing is, I doubt that you, in the worst case, let's see they're completely two different trees, right? Or let's see the subtree we're checking is basically, yeah, it's first of all, it's n, so this is S size, this is T size. Yeah, I doubt you can have quadratic complexity here because every time you check subtree, if at least one times it matches, you return true. If it doesn't match, like at least one element doesn't match, let's say the last one, then the chances are you have multiple subtrees everywhere at every level like this. So it's very weird topology maybe where you can achieve the asymptotic complexity equal S times T. In most cases, it will be just S size. So let's submit multiple times. We also don't modify them, so we can say const here. And then I believe we need const here. Const here. So we don't modify them. And then const here, obviously. Const here. Right, so we don't modify pointers. It wouldn't give us anything basically, but just to make sure. All right, still same memory, still same runtime. Third time, better, worse memory, okay. Oh man. All right, let's switch to the whiteboard so far and go, oops, to the point section. Today was easy problem, which is good. So we've got I would say decent scores, not the best one, but decent, 87 for time complexity. For space complexity is small one. Let me rerun one more time. Maybe, I don't understand, like they don't like the fact that I'm using Q here, I guess. But this is Q of pointers, so it's not like big a deal. Whatever. Let's try to submit one more time. See if we get something better. Now my runtime keeps dropping. It should be 20 milliseconds. Yes! Yes! I would stick, I guess, with... Let me see, can I get the best result here, like at all? Everything is worse now. No way. All right, one last check. And then I'll accept whatever memory I have. No, one more time. This time is the last one. Yes, the best possible results, the best possible combination. Let me switch this in. So you see how many runs I did here, right? I started 20 milliseconds, 24, 28, then 16 once, 28, 28, and then again 16 in terms of memory. 29.5, it was the lowest one. And again, we hit both here. So these are final scores, 97 and 15. So going to the board, so we just get extra 10 points here. This was, if I remember correctly, extra 3 points. So it's now 15, not 12. So the total one is 107 plus 5, 112. Correct? Yeah, 112. Nice. Something finally over 100. So maybe a little bit of smile here. Maybe a little bit of disappointment too. All right, let's go to the default scene. And where is my channel? Home. Some fireworks today because we did good. World's largest shell, whatever. Ooh, nice. When you can only solve easy problems. But damn, that was a day today. All right. Thanks everyone for watching, and hopefully see you next time.